Okay, good evening, everyone. For some reason, I'm not able to share the screen. I've asked permission from the host for doing that. I hope it says host disabled. Host disabled. So maybe I've not been made a host or something. So we'll.
So you can able to share now.
You can share now. Okay. All right. Okay. All right. I can share now. So this is the peer deck login. Please ensure that you're logged into peer deck as well. Let me see if people are joining there. Okay, so enough people have so I'll go over there'll be like roughly two parts or so to this session. First one will be based on a small survey that I'm going to conduct. So we'll sort of gather data and then try and do some simple statistical analysis on that data. I've done this a few times in the past and the students have gone away enjoying it. So let's see if that can be repeated now. So that's the first part. A few questions based on that. The questions will be similar to what you've seen before, except that the data now comes live from here. So let me see, about 85. So this should be giving us enough data. So I should do that next. Okay. So there are two links here. The first link has basically a list of formulae for various hypothesis tests and all that. I hope those are correct. And the next is the survey. Okay. So I hope you can go click on that survey form. You'll need an online degree login to access and respond. So once you click on the survey form, I hope you're able to go ahead and see this. So let me just see. Okay, there's at least one response now. Good. So I'll wait for a few responses to come in. So click on the survey form. There's like 4 questions, very easy to answer. I hope if you can answer that. So you can see the results are coming in. There's just four questions. One, maybe I should do this for this one to get the wrapping right. Okay. So do you attend live sessions? Do you actively participate in discourse discussions? How far is your center in kilometers? Enter your quiz on mark. So this is the question. So responses are coming in. So this is actually the data. And we will sort of do some analysis on this data. So go ahead, do that. Let me give this a couple of minutes more to gather enough data. So click on the survey form. Those of you who came in late, maybe somebody can put the survey form link on the chat window. Can someone do that? And also, I think, can you put the code, the peer deck code on the chat window? Okay, thank you. Someone's asking how did people get more than 80 marks in quiz? Just saw the survey. So there are people, many who get 100 out of 100 in case case you're wondering. So, okay, so let me just give it one more minute. So I see about 57 responses, 56 responses are going up. So you can see there's 98 and all that. I hope people are honest in responding. I think this attending live session 83% and all sounds really unreasonably high. Same thing with discourse forum 63%. Okay, what 66, 67 people have responded. I think I think you also have access to the responses, right? So I think let me I mean you will get it when I give you access. Okay. All right, so we've done the survey, we have enough data, we can look at it and study it if we want. So let me begin with the first question. So we are interested in estimating the fraction of learners who actively attend live sessions. So once again, let's start from the very basics for you to picture how this happens. There are 2,500 learners in Stats 2. We are not going to be able to reach everybody and ask them this question. If we could and we could ask, then there's no need for any statistics as such, because you have the actual complete data. So you know who all are attending, who all are not attending, right? So we only have access to a fraction of the learners, how many ever are here today live with us and attending the the survey and participating in the survey. Only those people we can ask, and from there we hope to estimate the actual fraction who are actually participating in live session. So this seems like I don't know if it seems like a reasonable process to you, but let me start with a very, very easy question. Which question number? You can answer a number here. Which question do you think is interesting or important for this estimation? There are only 4 questions you have to answer. Which one? Just a quick one for you to get started. There are only 3 responses so far. This is a very easy question to start with, so you should, I think, quickly give an answer to this question. Okay, so about 27 have responded. I think I should try to estimate what fraction of the people who are joining are actually active. It says 111 participants. There are only 67 people on peer deck. Maybe somebody can put the peer deck link once again in the chat. And number of people actually responding on peer deck is really, really less now. It's only like 30 out of 111, so to speak, right? So please join peer deck, log in. Then those of you who have not filled the survey form, you can also fill the survey form at this point. Let's have data. Okay, I'll wait here for maybe 1 more minute for people to catch up if they are joining late. Okay, the answer itself to this question, I think, is, I hope most of you would have gotten it right. It's okay, so let me stop at this point. Yeah, first question, I don't know, a lot of people are saying they'll use 4 questions. I think, why are question 3 and 4 and all relevant? I think it's the first question, right? Why is distance to the center relevant for attending live sessions? no, I thought only the first question, Okay, so fraction estimate is just from the first question. Nothing else is relevant to estimate this from the survey. Okay, so that's what you need to do. So now survey results. You can, if you want to see the results, you can click on this link. It will give you a sheet which has the survey results. So what is the sort of theoretical model that you're going to use to model the responses that we got in this survey? So if you go see this survey, this is the survey, this is the response, this is the first question, this part is relevant to you, and there are 79 responses, so to speak, and bunch of yeses and bunch of no's. And if you want to see the fraction of these things, it's very easy to see here. So it says out of the 72 responses, 64 are yes and 14 are no. Okay, 64 yes, 14 no. You can also, if you're comfortable with spreadsheets, you can quickly count. You don't have to manually count, by the way. It's very easy to count and get the thing. And I have a fancy little visualization here in the form, which tells you out of the 78 responses, you have these two. So I'm going to stop accepting responses so that the data sort of freezes. Oh, this is the data we have now. 64 have said yes, 14. So now, given this kind of a thing, what is your sort of sample model? No, nobody is really is wondering what is the sample model. Why are you asking us all these complicated questions? So basically, we are going to assume out of the total population of 2,500, we have randomly chosen, right, some 78 people. Okay, very randomly chosen 78 people out of this 2,500, and those are the people who responded to this survey. Okay, so supposing out of the, say, 2,500 or so, some fraction is actually attending live sessions, right? I have now these Bernoulli sort of random variables here, x1, x2 to x78, right? There are 78 of them. Each is Bernoulli with probability of 1 being this fraction that I'm interested in, right? If they said yes, then that would be 1, and if they said no, it would be 0, isn't it? That's the Bernoulli random variable, and that has a probability of success which is equal to this fraction, right? The overall fraction of people who are actively attending overall in the entire population. Is that okay? So that's the rough model, and sometimes these kind of models are good to keep in your head because that gives you a very good understanding of what is it that you're actually doing. Okay, so in this model, how will you estimate this fraction p? Okay, let's see the responses. If people are, okay, everybody's saying binomial. Yeah, each response is a Bernoulli p. I think somebody has said that very clearly. Each response is a Bernoulli p, and p is your fraction. Okay, a lot of people have said Bernoulli. Yeah, x1, x2, x78 is IID Bernoulli. This is perfect. This is the sort of sample model. It's perfect. It's not quite binomial. I guess if you add it up, you can say it's binomial, but sort of related, definitely. Okay. So now the question is, what fraction of the survey respondents actually said they were active? Okay, I gave you this answer, 64 out of 78, right? So that answer is very easy. So now, what is the method of moments estimate of this fraction over the entire set of students? What is the ML estimate? Okay, this is the question. It's a very easy question. Okay, let me wait for at least like 30 responses. I think people are not responding at all. I see about 89 are in peer deck. It's very interesting because 123 seem to be in Zoom. So not everybody who's in peer deck is in Zoom, is in peer deck, and not everybody who's in peer deck is responding. Okay, I felt this was a very easy question to start off with. So x1 to x78 is this IID Bernoulli. You got the zeros and ones. And how will you estimate P? We've seen this before, the method of moments estimate and the ML estimate, in fact, in this case will coincide. And, okay, so about 25. In the interest of time, let me just stop here. 0.82, yeah, 64 by 78. That's absolutely correct. 64 by 78. It's not 64, it's 64 by 78, 64 by 78. There you go. So it's a very clean answer to write down. It's just the sample mean, right? The sample mean would be equal to this estimate of P, etc. So now comes the interesting question, right? Do you really believe this number? Okay, there are instructors here logged into the chat. I think I should ask one of them to respond. I don't know if Nikita is there on the chat, the Zoom or not. So if you're there, do you really believe 82% of students of Stats 2 actively attend live sessions? Right? No instructor wants to say anything. Okay, maybe they're not there. Okay. So it's not really true. No, I mean it's 82 is probably not a good number. Anyway, mechanically, as far as the assumption is concerned, this is the answer. So what was wrong? Something was wrong in terms of it's either all of you sort of wanted to create this good impression that you're good students and you didn't want to reveal that this is not. I mean, I'm a good student. Many people are very careful about saying bad things about themselves. So they say that it's very true. And then, of course, it can also be that, the sample that we're seeing here is not really a random sample from the entire population. It's probably very representative of, not very representative of the average student who never comes. So these are all very important things in statistics. You should be very careful about how you sample and all that. A lot of time spent on that. But once you sample, you believe in the model, and then once you have the model, you have to come up with the answer based on the model. Those things are very mechanical, but whether the sample is good or not is an open question, very hard to answer. Okay, all right. So we will believe the sample and proceed, but keep this doubt the back of your mind. Okay. All right. So here's the next question. Okay, so assuming quiz 1 has like a pass mark of 40. Okay, anyone who got greater than or equal to 40 is deemed to have passed quiz 1. If you look at the survey results, using the survey results, how will you do an ML estimate for the fraction over the entire set of students? Yeah, survey, we have stopped accepting responses. We already have 78 responses. So I just wanted it to be frozen so that we work on the same set of data and we don't keep changing the data. Okay, so here's the marks. One person was at 0. A lot of people, there is a spread here. And you have to sort of convert it and figure out how many of this are less than 40, etc. Maybe you can do it here, right? So try to count this up to here. So the spread is big. So this might actually be a representative population for the score. No, this is distance. That's what I saw. Oh, this has stopped giving me the proper picture. Okay, so anyway, you'll have to now here look at this guy, and then maybe I can do a explore here. See the histogram here if you like. It has some numbers. It has its own bins. So 4 to 12 and something here. So it looks like roughly about 6, 18, and maybe 2 or 3 here, maybe. So about 20 seem to be below. I don't know. Is that the count? I don't know if somebody counted that with the spreadsheet formula. So there's a question here, which is a very complicated question. What do you mean by distribution of marks? Is a random distribution between 1 to 100. What is that? What is the meaning of that question? It's you have to think about that question carefully. What you asked. It's not very easy to answer that question. Let me proceed with this peer deck session. I'll come back and maybe attend to some questions later on. Okay. So there's only 14 responses to this question on peer deck. So I'm just wondering if people don't know how to add up. To do this, I don't know. Let me see. I'll wait for maybe a minute more. Okay. So once again, I think this is again asking about a fraction, and you have to look at the 78 responses and then count the number of people who got above 40 or below 40, whatever you want to count, and then divide by 78 or something, and you'll get this fraction, right? So this is what you're expecting. Once again, I think the assumption is there is a population and there is the number of people who got greater than 40 in quiz 1, and this 78 is an IID sort of sampling from there, and then it's done, right? Can we add it using Explore? Oh, on Explore you can't add. I think you need like a formula here. I don't know if you use spreadsheets that much. There is a formula you can use to add. I think people have, maybe you don't know how to do that, and I think you're in a data science program and you have to learn how to do this, right? So maybe I'll have to do this. No, COUNTIF, yeah, COUNTIF, SUMIF. There's lots of interesting things you can do. You can also sort the column. There's so many interesting ways in which you can quickly count this on the thing. So let me see if people have actually done that. Yes, the responses. Yeah, here you go. So this is a very nice summary of how to do this. Each response is Bernoulli P. P is the fraction of students who passed, right? So if you assume x1 to x78 is IID Bernoulli P1, if marks is greater than the ML estimate is 0.76. Okay. Okay, don't know. Okay. So 20 by 78 is people who got less than 40. I think the other one, I think it's 59 or so by 78 as believable. This is the number of people who got above 40. Looks like 59 by 78 is happening quite often. So that seems to be a believable sort of number. So what do you think is the actual fraction? You think it's actually 59 out of 78.76? You think 75% of the people passed in quiz 1? So again, I think the actual number is close to 55 or so. No, I think I'm saying yes, it's not true. The actual number in the population is about 55 or so. So again, we used a statistical method where only people who do very well are attending these kind of live sessions live and interacting. People who are not doing well probably give this, and that seems to be biasing our responses here. Okay, so this is something to keep in mind. Hopefully you got your feet wet with a little bit of simple calculation. So let's do slightly more complex calculation. So here is a parameter estimation problem. So you saw the results, and we're going to assume that the distance to exam center for the entire population, some sort of a normal distribution with mean mu and variance sigma square. Okay. and you have to now look at the data. You have a sampling now, right? So you have x1 to x78, and x1 to x78 is now what? IID, normal, mean, mu, variance, sigma square. Okay, so how will you do ML estimate of mu and sigma square here, right? So this is, here's the data. This is not a very good fit with normal, I think, right? So if you look at the histogram here, not really a great fit with normal. These heavy tails on both sides. Usually normal will come down much more steep, but you know, it's the best we can do quite often. So a lot of times, even when the distribution is not very normal looking, people make the assumption of normal. Sometimes when you have wild distributions like this with a big spread, it's better to do you know, take some sort of a log and then do normal. So that's also something possible. You could do that, but nevertheless, I think once we fix the model, we can just work with the model. This is a bit of a more difficult calculation, but Excel, I mean, I think Google Sheet has a formula here. I think if I just select this, it will tell you here average is right there, 67.8 kilometers. And maybe if you explore, you can find variance of column D, I can ask, I think. Oops, it's some big, I think maybe I should ask standard deviation. So it says 187, but it looks really high, right? I think someone travels 1,600. Oh, somebody has put a crazy number like 1,600. Okay, I think that's the problem, right? Apparently one number is 1,600. I don't know who this person is. He's got 82 marks. He's traveling really 1,600. Should I edit it? Whoever it is, can't be 1,600, right? Really? I think that's the thing which is completely messing up the data a little bit. So normally when you collect data like this, you would go look at that 1,600 and simply drop it, right? So you will not use that data. So you have to really pick those things out and not use it in the data. So anyway, I mean, it's just textbook problems for us. So what you do is just the mean and the variance, and that would give us the estimate. I think most people have not responded. I just did it for you. It's about the average of all of these things. So it's about 67, and the standard deviation ends up being really, really high. Maybe one can change it, etc. So anyway, so this is sort of one more example on how these kind of calculations are done, and how do you use these parameters. You may wonder what's the point of using these parameters. If you believe in this model, you can use it to you know, do more calculations. Like for instance, you can try to estimate what fraction of students are within a distance d of their houses. You can try that, you know, and this d, whatever d I give you, I mean, I could tell you d could be 100, right? So if you say 100, then what would be the answer? Let's say d is 100 here. This d equals 100. Okay, so mu ended up being, you saw, so some 67 or something, and then sigma was something huge because of that 160. I think you should 1,600. Maybe you should just ignore that and then use some other sigma. I don't know. So if you have to do d equals 100, the fraction of people who are within a distance d of their houses, you can measure these things, right? So so you can do calculations of this sort once you have an estimate of the parameters. Okay, in the population now, right? So you did only 78 survey, then the population is some 2,500 or so, and we are using that in some sense for this. Okay, so I hope this is clear. I think let me move on. I think it was just to show how for some data, you assume a certain model and then extract parameters and then use it in some interesting way. Okay, so let's move on. Let's move on to some testing. Here is a testing. Okay, yeah, sure. I think if you change that 1600 to something else, it's making some direction. Okay, so here's a question. Here's a testing question now, based on once again this survey data. So I'm saying the fraction of students who participate in this course is actually 50, 0.5. So that's my statement. Okay, so I'm giving you a statement that the fraction of students who I think in stats 2 participating in this course is 0.5, and maybe you have a suspicion that it's actually larger, right? Let me just check this very quickly. 50 is a, yeah, it's okay. Okay, so you have a suspicion that maybe the fraction is larger, and you can use the survey and the questions that are there. So think about this scenario and ask for what will your null and alternative hypothesis be? What is your test? What is your test statistic? You don't need to use the survey results actually for this question. It's just, it's not yet. Maybe in the next step you may have to, but at this point it's just stating the null alternative and naming your test, coming up with the test statistic. Okay, so about 25 people have responded. We wait for a minute more. Let's see. Okay, so let's see the responses. Yeah, okay. So binomial H0 is P naught is 0.5, HA is P naught is greater than 0.5, reject null is Y is greater than C. Yeah, so I think some test like this, you can also do it instead of just doing it with Y, you can also divide by N and then do it. That's also okay. Both of these are good. Yeah, mu equals 0.5, greater than 0.5. So you can do it with P. This is all Bernoulli, right? So it's not a Gaussian distribution. Not less than P naught greater. So usually the null hypothesis is taken as a simple. This is good, right? H naught is P equals 0.5, P greater than 0.5. So yeah, so you'll end up using some sort of a right-sided t-test. This is not given to you. Yeah, this is good. Yeah, the test will come out as reject H naught if X bar is greater than C. This is correct. Okay, so I hope this is something. So the first part, I think for people who are joining in late, the first part is the survey part, is not representative of what you'll be asked in the exam. Of course, these kind of questions may come, but not with survey and all. Okay, so no need to worry about survey. It's just for your understanding and improving your use of statistical methods, nothing more. Okay, here's the next question. So a question like this can be asked even in the exam, right? So what is your conclusion at a significance level of 0.05? Do you accept the null or reject the null? Given the data from the survey. Now we are using the survey, and I can show you what the survey said. Survey says 49 out of 78 actively participate, and 29 out of 78 say they do not participate actively in discourse discussion. So 49 out of 78, the survey says participate, and 29 out of 78, the survey says they don't participate. Okay. 49 say yes. Okay, you don't have to actually use some t distribution or normal distribution. I think it's you can leave it in an equation where you maybe don't simplify the probabilities. You can say if this calculation ends up being greater, it's enough if you leave it like that. So for Bernoulli distribution, the mean and variance are easy to find, right? So it's NP and then NP into 1 minus P, right? So once you have that, you can use, I mean, you can either use the binomial formula, it's too complicated to calculate, or you can use a normal approximation with that mean and variance. It won't be too bad. It will give you reasonable answers. So you can set it up in that fashion also if you like. So the alternative hypothesis is basically based on the suspicion that you have, right? So the null hypothesis is that this fraction is equal to 0.5. That is the statement. This P naught I gave you, P naught equals 0.5. So your suspicion is the fraction is actually larger. Then for every suspicion, you'll have an alternative. If you suspect it to be larger, then it will be the HA is that P is greater than 0.5, and your test will be based on the right side top of test, right? So you'll reject null if the test statistic becomes greater than C, right? That's the way it goes. And why it's not T less than C? Okay, so basically the null hypothesis is that P is 0.5, right? P naught is 0.5, and your alternative is P naught is greater than 0.5. That's your suspicion. You're suspecting that the actual fraction is greater. Okay. If the alternative is true, then you will get a larger fraction of people who will who would have said that they participate in discourse, right? So if you get a larger value of people saying they participate in discourse, then you're going to probably reject the null, right? As in, you'll accept the alternative because your suspicion is it's greater. So that's why you build a test statistic, and then if the test statistic is greater than C, you choose the alternative. Okay, so that's sort of the maybe intuitive reason as to why for these type of alternative hypothesis you are getting a test of the form T greater than C. So the right side comes from that point of view. Okay. If on the other hand, if you are suspecting that the actual fraction is lesser, then your test would go T less than C. Yeah, so that's the sort of intuition in some sense. Okay, so let's see what people have typed out. About 14 people have responded. Okay, reject, accept, reject. Okay, yeah, so this looks like a reasonable way to do that. So I think type 1 error has been computed here, right? Why C minus 49? I'm a little confused by that. C minus 49. Okay. Okay. Okay, so there's enough confusing answers. So let me maybe go on to a Jamboard and sort of write out what I think is the way this could be done. So basically, you're looking at a scenario where you have x1 to x78 are IID Bernoulli P. And your null is P equals 0.5. And your alternative is P greater than 0.5. You come up with a test statistic, which is x1 plus, let's say, x78, right? And you say your test is to reject H0 if P is greater than C, okay? And your alpha, which is a significant level, you want this to be 0.05. It's probability that you reject H0 given H0 is true, right? So once H0 is true, what is the value of P? Okay, so there is a point, yeah, P would be 0.5. So I mean, people are talking about Z test and T test and all that. So usually, I mean, those things come in the normal sample type assumption. So here, your distribution is well known. It's a binomial distribution for x1 to x78, right? So this would be probability that binomial of 78, 0.5 is greater than C. Okay. Is that all right? So if you want, you can approximate this binomial by normal 78 into 0.5, comma, variance will be 78 into 0.5 into 1 minus 0.5. Okay, so this is a very common approximation which is done, right? So you can do that. So this will give you a calculation for this this thing being FC. Okay, this is greater, so you will get 1 minus FC. C minus 78 into 0.5, that's where the 49 came from, divided by square root of 49 into half, right? So that would be 24.5 or something, right? Maybe this is what one of the answers was, I can't remember. Okay, so what is alpha? Alpha I want to be 0.05. So you solve for C using this equation. Okay, so this is roughly, okay, so this is approximation. If you want, you can do the binomial exactly. So this T test versus Z test, it's not something that you apply usually when you do these fractions and binomials, right? So it's a the distribution itself. So you just do the exact calculations in some sense. Okay, so from here we find C. Okay, is that all right? So So now if you look at the thing, it says, oh, so sorry, I think my calculation was totally wrong. It's 39, you're right, absolutely you're right. 39 and then one, it's just so late in the day, so 19.5, you're right, okay. So it's correct. So I got misled because it's 49 out of 78, which was, it came out here. So now, I don't know what the value of C is. Is anyone sharp enough to do this calculation fast? So C would be 39 plus square root of 19.5 times FC inverse of 0.95. So by now you should know what FC inverse of 0.95 is, right? What is FC inverse of 0.95?
1.645.
Yeah, you must know that. So what is square root of 19.5? It's a simple calculation. You'll get roughly, this is about some 4.5 or so, and then this is a little higher than that, times 1.6 is maybe about 7. So this is working out to something like 46 or so. I don't know. Did anybody do this? 46.78. There you go. Not bad of a calculation. And your actual test statistic from the sample is ended up being what? T equals 49, right? Since that is greater than C, what do you have to do? You end up rejecting H naught. Okay, so your conclusion is based on 0.09, 0.05 significance level, you're getting this to be. Is that okay? Okay, so this is for fractions and testing. This is what you do. You don't have to worry about. I know there is a Z test and T test and all that. Usually that's for normal samples. Okay, those are standard terminologies. The T test and all applies clearly for normal samples, right? The distribution comes from the normal samples property. Okay, so when you do binomial, there's only the approximation involved in the computation. Otherwise, it's just Bernoulli and binomial distribution to calculate these. Why have we not subtracted C with 0.5? We didn't quite get that question. Why would you want to subtract 0.5? So that's if you see, okay, so if you define your test statistic as the ratio, okay, if you divide by n or something, then you have to do it, but it's all the same, right? See, remember, this is Bernoulli samples, right? It's not normal samples. I'm dealing with Bernoulli samples. I'm just doing a normal approximation to the binomial distribution for computation purposes. I'm not saying my samples are normal. Like I don't have this T test and other tests coming in here. It's just Bernoulli samples. Okay, keep that in mind. So you just write down the test as reject H naught if T is greater than C. T is just the sum. Is that okay? Okay. Think about how this calculation goes. This would be okay. So this is a hypothesis test where you had Bernoulli distribution. I think in the very beginning, maybe in the previous week or 2 weeks back, I had done some examples like this. I think you should go back and look at it. Now, maybe with normal samples, you would do other things. This is Bernoulli. You have a binomial distribution for your test statistic. You do different calculations. Okay, so I think maybe somebody has done this correctly. Now that I go back and see, I don't see a C minus 39 at all. Nobody has done a C minus 39. So yeah, so there is a 46.78. Somebody has got that right. So good. Some people have done that, but I think this is something to be careful about. Okay, so here is the next one, which is asking you for the power against the alternative that fraction is P naught plus 0.1 instead of 0.5. If you say 0.6, why we have not divided by n? Okay, so you can divide by n also. I think it's fine if you divide by n also. Yeah, I think you can divide by n, and then I think the whole thing just gets multiplied by n, right? Isn't it? Did I make, is that okay? Or what happens in that case? So everything will get divided by n, no? So if you can just divide this binomial by n on left side and c by n on, I mean, it's just division by n. It's not going to change the nature of these results in any way. Instead of c being 46.78, it will be 46.78 divided by 78. It's all equivalent whether you divide by n or not. Okay, it's not different. All right, don't worry about that division by n. Okay, so what is the power calculation now? Remember the power calculation, right? Power is basically probability of rejecting null given that the alternative is true. Okay, and power usually is with respect to a simple alternative. And what is the simple alternative I'm talking about here? The alternative is that the fraction is 0.6. It's not 0.5 is null. And we found a C of 46, right? Now the power is computed against the alternative that the actual fraction is 0.6. So you have to find probability that you reject null. When will you reject null? That T is greater than C, given that the alternative is true. Alternative is P equals 0.6, right? So that's the calculation you have to do. And that again, you can approximate with a normal to do a simple calculation. So I don't know if people are comfortable. You can leave the answer in terms of an FC if you like. Let me see if somebody gets it right. Somebody wants to know if level of n term is like mock. I think I haven't seen the mock myself personally, so I'm not able to comment. I think it's generally similar to the mock. We don't change it very differently. Yeah, beta is accept null when alternative is true. So power is 1 minus beta. So that is probability of reject null given alternative is true. Yeah, so Nikita has responded on the chat. So this mock is almost the same level, maybe simpler. Okay. So type 2 error is beta, and that is probability that you accept null given HA is true. Power is 1 minus beta, and that is probability of rejecting null given alternative is true. Okay, leave your answer in terms of FC here. I mean, approximate, there'll be a binomial expression. If you want, you can leave it as binomial also. But you can approximate the binomial with a normal and leave the answer in terms of an FC. Okay, so about 7 responses and they're coming in so slowly. So let me just see. There you go. Maybe there is something here. So maybe I should just quickly write it down here. Let me see. We'll do it here on this side. 1 minus beta, which is power, is probability of rejecting H naught given HA is true. And the alternative, so the alternative against which power is being calculated is P equals 0.6, right? So this is probability that you reject H0 if T is greater than C, given that P is 0.6, right? So that's the same as probability that binomial 78, 0.6 is going to be greater than C. Okay, so this one you approximate it as normal mean 78 into 0.6, right? Comma variance 78 into 0.6 into 0.4. Okay, so any quick answers on this? What is 78 into 0.6? It'll end up being some 46.4. Is that correct?
6.8.
8. Okay, sorry. Okay, and this one is what? Sigma equals, if you take square root,
4.32.
4.32. Okay, so 18.72. That's the sigma is 4.32. So approximately this probability is 1 minus fc of c minus 46.8 divided by 4.3. Is that correct? Yeah. Oh, this is like really very close to 0.5. Okay, we don't have that much. We also divide by n. I mean, where is the division of n? Did I make any? What division of n do you want? Everybody seems to want a division by n.
Yeah, actually they are asking about in the denominator.
Which denominator?
Inside the FC bracket, C minus 46.8 divided by 4.3 divided by n. I think that's where they are asking. I'm not sure.
Okay. Oh, you're right.
Samples, yeah.
I'm sorry?
That's done for normal samples. Generally, we do sigma by root n. They are asking.
Okay. So if you take the test statistic as okay. I think I know where you're coming from. So if you take your test statistic as x1 plus x78 divided by n, right? I think, see, how do you approximate a binomial 78, 0.5? I think it's normal NP and NP into 1 minus P, right? There's no by n there. If you divide by n, let's say you divide x1 plus x78 by n, then you will have a binomial by 78 being approximated as normal 0.5, and then you will have 0.5 into 1 minus 0.5. You won't have the 78 multiplied. Is that okay? That's where your division by n will come. Is that okay? So I'm not taking my test statistic to be x1 plus x78 divided by n. So I don't get the 1 by n there. Okay, so you get the by n only if you, I think you're so used to the test statistic being x bar that you're asking this question naturally.
Yes, sir. This is it. Because we are using x bar most of the time.
Yeah. If you use x bar, you can write the same thing in terms of x bar, and then you will get all that. But now it's not x bar, right? I'm using just the whole thing.
And it will be convenient if you clarify where we should use it, if it is Bernoulli case, if it is a normal case, then what test we should apply. It would be convenient.
Yeah. So in Bernoulli, usually you don't. There's no names for these tests when you have these Bernoullis, right? So you have to just go back to the basics of hypothesis testing and just use reject H0. And then only a normal approximation you make is if the n is very large, you simply approximate it as normal. That's all. That's what you do. When you go to normal samples, when you're approximating the samples by normal, you get all these z test and t test and chi-squared test, because all those t distribution, chi-square distribution comes from the normal. When you add there is the t distribution and the chi-square comes as the sum of square of Gaussians, right? So the the distribution of the sample mean and the distribution of the sample variance is the chi-squared and the t, right, for the normal samples. So that's where those things come from. Okay.
Okay, fine, sir. We have to go through
Okay.
that.
Yeah. So there's one more doubt a lot of people have, particularly in this class, because I emphasize this root n type thing a lot. Okay. See, remember, if you have x1 to xn being IID, right? If you want to approximate x1 plus xn,
We can't see your screen, sir.
yeah, sorry, I'm writing something up. Apologize for that. So if you have x1 plus xn being IID, and you want to approximate this some Sn as x1 plus xn as a normal distribution, you can just directly approximate it as, so let's say mu equals expected value of x, and then sigma square is variance of x, right? The distribution, each xi, okay? So you can just directly approximate this as n mu and n sigma square, okay? There's nothing wrong in this approximation. This is how people do normal approximation, okay? I think somehow, I talk a lot about this pi n and pi root n from a convergence point of view. See, when you say, so why is this not a good convergence result? Because things are blowing up with n, with n, the right hand side blows up. If n goes to 1,000, 10,000, 100,000, your mean goes to some 100,000 times mu, variance is also blowing up. Normally, when you state a mathematically precise convergence result, you can't say things are blowing up and say it is convergence. Nobody will accept its convergence. So to get that correct convergence to something finite, what do you have to do? You have to divide by either n, which means it will converge to the mean mu, or you divide by root n, which means it converges to some normal distribution. So that's the way I describe it, the convergence. But it doesn't mean that the normal approximation works only when you divide by root n or something, right? You don't have to necessarily do it. If you divide by root n, then you will get manageable expressions to compute. Your mean will be mu, which is small. Your sigma square will be sigma square, which is small. But just for purposes of writing, you can just approximate like this. I know my n mu is blowing up, n sigma square is blowing up. It's ugly and big in calculation, but the approximation this way is easier to write down. It's valid. It's not wrong in the approximation. Okay. So, okay. All right, let's come back to these questions. So this is again a binomial type distribution Bernoulli testing problem. You don't have to use your t-tests and all these other tests here. Okay. All right, we come now to the next test. Here there are no calculations. It's only a purely qualitative question. I want you to think about the survey that we did and see if you can test for a statement that I've made here. Okay, the statement that has been made here is, I don't know if you believe in the statement or not. The statement says, learners participating in discourse forum score higher marks in quizzes on average than those who do not. Okay. So let's say the variance of scores is given to you. It's known to you. Okay. So now all your assumptions will start. Okay. So now you have to start assuming some Gaussian normal distributions and all that, right? So now all your terminology of Z test and T test and all those things will enter the picture. Okay. So I want you to think about this question and answer this for me. So what data from the survey will you use? How will you use the data? Is this a one sample test or a two sample test? What is the test? What is the test statistic? How will you go about doing this? So here we'll assume normal samples from the survey. See a few responses coming in. Okay, so let me just quickly show the responses here. About 20 plus responses have come in. There you go. 2 samples, yeah. One sample is discourses, yes. Another is no. Null is okay. Okay. Null is not null. Usually, we always take null as a simple hypothesis. Okay, so to keep that as a general rule of thumb, and of course, there's no hard and fast rule there, but usually you always take null as the simple hypothesis, and you can do that. And how do you calculate for samples? How many? So remember, how many samples do you have for S, and how many samples do you have for no? Right? It's okay. Somebody says F test. Why is this an F test? This is a 2 sample Z test, right? I'm only interested in the average here on average score. And if you look at N1 and N2, right, you have 2 samples. What is N1 and N2? In the S side on the discourse, you have 49. On the no side, you have 29. Okay, it's 49 and 29. So you have that many samples. The number of samples you go are not different, but it's not the F test. Remember, F test is for variance. If I'm talking about the spread of the pro courses of the marks or something, then you do F test. If this is just on average, the people who participate in discourse do better in the quizzes is the question. Okay. So you have 49 people in the one thing, you have 29 in the other, and you're going to do a 2 sample Z test. I've said variance is known, so it's not given to you, it's known. So this is the thing. So HA, what will be the alternative? Mu1 will be greater than mu2, right? So that's the alternative. So whoever is typing, please type mu1 greater than mu2. Okay. So yeah, the next one is here. Yeah, it's here. The one below that is also very precise. So this is how it goes. Okay. So I hope we didn't really discuss a 2 sample t test in class, but you could use a 2 sample t test also if you want to. But in this case, I've assumed in one of the statements, you can see in the question that I've assume variances of scores are known. Okay, so I've asked you to assume the variances are known. They're not given here, right? But I've assumed they are known. So of course, in practice, you'll have to use some sort of a t substance. Okay. Okay, good. I hope this was clear. So there's a similar question next. Okay, people are quickly writing down the answers. I think it's quite okay. I think somebody had asked something similar. I mentioned something about the spread in the previous question, so I think it's probably a dead giveaway. Everybody knows what to write now. Let me wait for some 20-25 answers. Sure. Okay, so about 20 people have responded. Yeah, so this is the F test. You know what distribution to use, right? This 49, 29, in case you want to use it. H0 is sigma 1 equals sigma 2, HA is sigma 1 greater than sigma 2, or what is sigma 1 for you? Okay, there you go. This is probably cleaner. 2 sample F test. The F test is missing. Mu1, oh, it's still mu1. Okay, do not want a sigma 1. Okay, so this should be standard deviation, variance, and all that. Except the only thing I don't like here is what is sigma 1, what sigma 2 is not there. So sigma 1 should, if you say sigma 1 is greater than sigma 2, sigma 1 must be the variance of people who do not attend live sessions, right? So you're saying, the people who attend live sessions have lesser spread. So the variance is smaller. That's what we are saying. Okay. So that's good. Okay, good. So this is that. Okay, so this brings us to the end of the first part, I think, of our, So first part was based on the survey. I hope it gave you a glimpse of how things actually work in many statistical methods and use of statistical methods. How people do it, except they would, I think they would survey much better than, or maybe they don't. You see all sorts of surveys these days, but you should survey better than what we did here today. I think only the interested people are here, active people are here, so it's not a very representative sample of the entire population in some sense, but if you do a good sampling, you will get something. Okay, the next few questions are a little bit more typical, more like your mock question and more like what you can expect maybe from the exam. Here's a question. Okay, the answers are inching up to 17. Let me wait for just 3 more answers to come in and clear it out. So this has got only one parameter, right? The distribution has only one parameter P. So you just have to write one equation in method of moments. You write that the sample mean equals the distribution mean, right? So the distribution mean is, you calculate expected value of X. That will be a formula in terms of P. You equate it to the sample mean, and the sample mean in this case, you can just add and divide by 8, which is the number of samples. That's just a straightforward calculation for this. Okay, so now entries across 24. So it looks like 5 by 8, 0.75 minus 0.87. See, when I see an answer like this, I get really, really scared. Okay, this minus 0.87 is simply not going to be a very valid answer. No? We are at the end of the day estimating some sort of a probability here. 0.75 is the largest, and so 1.54 again. You know, we've had answers like this in something. I think that you're doing some Gaussian and all that. Where does Gaussian and all come from? Where did minus 0.87 come from? I'm really mystified by that. You should know some mistake has happened. No, if you get minus 0.87 or 1.54, it's unlikely. I mean, this we do some really crazy samples. It may not have happened. 0.75 seems to be again 1.3. Again, these are all hints that maybe your answer is wrong. You have to go in and check, right? 0.75. Many people have got 0.75. So 0.75 is popular. Many people are going out and rewriting their answer as 0.75. I hope you get this right. I think if you do the mean, you just multiply 1 with this and add. I think you get 1 plus 7p by 6. Is that correct? Hope that's correct. You get like 1 plus 7p by 6. That's the distribution expectation. And then you have to equate it to the sample mean. Sample mean is 15 by 8, I think.
Yes,
Right? So you take 1 to that side, you get 7p by 6 is 7 by 8. And 7 cancels. 6 goes to this side, you get p as 3 by 4. So 0.75 is the correct answer here. Bread and butter method, these kind of methods you should know really well. Suspect your calculation if you get answers like negative for a p like this. See, p is, why should p be positive, right? So p by 4 is like probability of 0, and if you get minus 0.87, that's not correct, right? And if why can't p go above 1? Look at this 1 minus p, right? Then this probability will go negative. It's very unlikely that you will get such answers, no? So think that through and then check your steps carefully. Okay. What about ML estimate? Don't put your answers on the chat box. Somebody should post the peer deck link again. I think there's been. Maybe I should. Okay, so this question from Advait to me wants to know if there's some general conditions under which ML and ML and method of moments and maximum likelihood are the same or different. As far as I know, I don't think there are very generic. I think maybe there are some sufficient conditions, but I don't know. I haven't come across any very neat and generic condition. I would say it's unlikely to exist. I think there's various cases where it doesn't exist, so it may not be a very slick, easy condition to check these things. Okay, some 17 have responded. Let me wait for like a few more. When the number of responses crosses 20, I'll start sharing. Okay, so we have about 20 responses. Let me see if, okay, 0.625, that's, please give this questions. Okay, so 0.75, 0.625, I believe is 5 by 8, right? Yeah, that's correct. So 5 by 8 is, I think, is correct. This is very easy to do. So likelihood of the samples is just product of all their probabilities, right? So you will get here 1 minus p times p times p by 4, okay, times p by 6, so on. So overall, if you see, it will work out, the likelihood will work out to p power 5 times 1 minus p power 3, isn't it? That's what this will work out to, right? P power 5 into 1 minus p power 3. Of course, there'll be some division by something. It's not so relevant to us, right? And you have to find the p that maximizes that. You can take log, etc., do all that, or from your experience, quickly know that the answer will be 5 by 8, right? So you would have done this kind of problem before. It's very easy to do these things. Okay, so this is ML estimate. Let's move on. We are the last 3 questions. The next one is Bayesian estimate of P under a uniform prior. Bayesian estimate with a uniform prior on P. People are taking a long time to answer this question. I'd imagine if you've been solving problems, looking at that, I think it's very, very likely you've seen a problem like this before. It's very standard, typical question in this area. Okay, so only 14 responses have come in. Let me wait for a few more. 1 more minute, maybe. Okay, somebody wants to see this demonstrated. Okay, let me just see the answers. About 18 people have answered 0.4, 0.6, 0.6, 0.6. I think 0.6 is correct. It's something that I know before. Maybe I should write it down. So let's let's look at this. X is 0, 1, 2, 3, 4, and then Px is, correct me if I'm wrong, it's P by 4, 1 minus P, P by 4, P by 3, P by 6. I hope that's correct. And the samples are samples. The samples, it's 1, 0, 4, 3, 1, 1, 2, 3. Okay, so this is bread and butter problem solving. So if you want to do method of moments, you have to equate expected value of x, which is, if you calculate, you will get 1 plus 7p by 6. That to 15 by 8, that will give you p hat mm to be 3 by 4.75, if you like. Then ml is min argument of min. P hat ml is argument of minimum over p of likelihood. So it's p by so p power 5 times 1 minus p power 3, and that will work out to 5 by 8.625. Now for Bayesian with uniform, so let me just warn you, if you're seeing this for the very first time, you should definitely go see the lectures and learn and come prepared. This is like bread and butter, very basic stuff. Try to read this up. This is easy enough. So the posterior is proportional to the prior, which is just 1, times the likelihood, which is already there, p power 5 into 1 minus p power 3. See, remember, in this likelihood, there are some constants here in the denominator. All of that don't matter. So the posterior is beta 6, 4, right? Right? So posterior mean, so p hat Bayesian uniform is posterior mean, which is 6 by 6 plus 4, which is 0.6. So, okay, any questions on this? I hope this is clear to you. It should hardly ever take, if you're really experienced with the stuff, you'll be done with this in like less than a minute. Okay. So make sure you do at least, I think I'm reasonably sure I do a workload example exactly like this in my lectures. I think it's very likely that many activity questions, practice questions have this. So this should be done. Okay. Okay. So that's the interesting question, isn't it? So what do you pick? I mean, you have 0.75, 0.625, 0.6. What do you pick? What do you pick? No, nobody wants to commit to anything. Bayesian, or there's one person who's willing to risk the Bayesian estimate. Anyone else? Bayesian, everybody seems to like Bayesian. Average of all three. Okay, so generally, roll a die. Yeah, it's fine. I think it's difficult to say. You know, I mean, it's very hard to say which one is the best. Yeah, some people will fight and pick either the first one or the second one. A lot of people like ML. ML is present, which is marketable. Yeah, that's true. Present whatever helps the case of your product the most. You know, I think that's more or less what most people do. And in some sense, they keep changing your prior till you get the most desirable answer. You know, you can make the prior whatever you want. It's okay. I think these kind of problems show you that there is a wide variety of ways to do statistical estimates, and it changes from time to time. And generally, if there are very few samples, then I think the best would be to bias based on experience and do something. I think that's usually something that's done. If you have even reasonable number of samples these days, ML is a pretty good method. Very sophisticated ways to do ML better. Anyway, So let's move on to the last set of questions. They're both from testing, I think. Okay, the first one is on informative priors. Again, this is, I think, very similar to a question I've done probably in my own lecture, but I guess people don't necessarily watch lectures. So let's see. So these are typical scenarios where you may want to use informative priors, right? See, in your own data, there are very few samples, 10 patients you're able to test, right, in a small place. And so you want to use some, bias based on prior knowledge. Maybe this has been tested in so many other places with many patients. And so you like that 80%, right? So why not? And of course, there is always care you have to take. These other cities cannot be in other countries with very different genetic signature than the city in which you're testing the new one. All those things, that's what I meant by saying expert knowledge of another kind. So you have to use a lot of care in this part of statistic as to what method you're picking. Once you pick the method, like I've picked for you here, I picked the method for you. So once you pick the method, it's more or less trivial today to do these calculations, and you should know how these calculations are done. But this is a typical case where you may want to use some informative prior from past experience. You can get much better results typically from this. Of course, if you biased it the wrong way, you'll go all over the place. What about, okay, somebody wants to know if hypergeometric distribution will come in the exam. These live sessions are not meant to reveal exam questions, okay? So I'm not going to comment on it. The exam syllabus is known to you, and we've also said there will be a slightly more emphasis on the last part, but of course, you'll cover the whole syllabus, okay? Okay, so there's a question from Naresh. Think about that a little bit, right? So it says prior is 1, prior is uniform. Yes, true. We're using just a flat prior there. And so the posterior distribution becomes, the expression is the same as that of the maximum likelihood, but the thinking is very different, right? In the Bayesian sense, this P is a random variable. And in the maximum likelihood sense, there's no randomness. It's just an expression, right? So these are very different things from a thought point of view. So you can't say equal in that sense, but yes, the posterior is proportional to the maximum likelihood because the prior is flat. All right, about 5 people are responding here. So see, once again, how do you pick? There's only one parameter in the prior to pick, right? You're picking a beta 3b prior. And why beta? Because any fraction, typically you will pick beta. What else can you pick? And I've just picked beta 3b. Why 3? Why not something else? If you have more pieces of information, I can pick it in a more smarter way. I have only one piece of information, which is 0.8. This is what I'm expecting. So I can pick a beta and bias it to have a mean of 0.8. Okay, so how am I biasing my beta? I'm picking 3, b, and I want expected value of my beta distribution to be 0.8. Okay, and that rule will just give you what value you'd pick for b, right? So I think, and beta distribution's mean is 3 by 3 plus b, right? So 3 by 3 plus b has to be equal to 0.8, and that gives you, I don't know, some value for b, whatever value you get here. Let me see if people are getting, everybody's getting 2. Some people are getting 1, some people are getting 3 by 4. I think,
Actually, we have used the 6 by 10 as, I mean, in the new town, 10 patients are tested with new drug and 6.
No, see, that's why you have to be very careful. You shouldn't use 6 by 10. See, that's this sample, right? This is your new sample, right? You have x1, x2, x6, which is distributed IID Bernoulli P. Okay. If you use just 6 by 10, 10 is just such a few number of samples. You don't really have confidence, right? You do p-value or something, you get very low numbers, very bad numbers. You won't have confidence in that. When you have those kind of situations, you should try and bias the beta towards the expected mean from the previous experiments, from your current existing knowledge from before, not from this sample. Don't use the same sample to bias itself. That's never a good idea, okay? So always the bias will come based on the previous information you have. From the previous information, you expect that the fraction should be about 0.8, isn't it? So I'm now going to bias with a beta which has an expected value 0.8. That's I think the most reasonable thing to do. At least I think that's what I've done in my example in the lecture. So you should follow that, and that's at least as far as the exam is concerned, as far as tests are concerned, it's very reasonable thing that you can do. Okay, so I hope this is clear. So maybe I should write this up. Too many people are asking me this question, so let me see if people have done that. A lot of people are getting 0.75. I think 0.75 is correct. 0.75 will end up being the correct answer. Okay. I hope you see what is done here. So my samples are x1 to x6. No, x10, right? X10, sorry, x10. IID Bernoulli P. And I'm going to say P is beta 3b, and I want 3 by 3 plus b to be 0.8. So this gives me, I think, b equals 0.7. Okay. So that's the sort of bias that you give here, and then if this is the bias you're using. So you see here, so yeah, because I have very few samples, I want to bias towards something and hope that this is correct. Otherwise, 6 by 10 is likely to be, all over the place. I don't know if that's a very nice answer or not for my estimate, right? So maybe you can use this bias. Okay, the last question of the day is basically using the above prior. What is the Bayesian estimate for the fraction? But this rule, you remember, I mean, if you have samples, never bias the prior based on the sample itself. The prior is supposed to be sort of prior, right? Before you sampled, you should have some opinion or belief about what where your values of the unknown theta are likely to be, and put a distribution on that. Okay, keep that in mind. I think don't do this. In fact, what some people would do in some problems is take a sample, take half the sample and bias it with this and that. I think it's all dangerous things to do. If you really know them well, you can do, but otherwise slippery slopes thing. But if it's well established from many other towns which are very similar to this town that you are interested in, then I think it's okay to bias. You get reasonable answers. Oh, okay. So this 0.75 is ugly, right? So I think can't quite use 0.75, no? So this point, maybe I didn't choose my thing carefully. So let's change the. Apologize for this. Change this 3 to 2. I think I should have been careful there. I apologize. Maybe change the 3 to 2. Okay, so maybe use a beta 2b prior. Is that going to give you something greater than 1? I don't want something less than 1. That's ugly. So what happens if I do this? No, that will become worse. No, so maybe I should make it bigger than 3. Apologize for that. So maybe you want to use a very high value for this 3. So make it 4 or something. No? Yeah, make it 4. So only. I want some value for b which is bigger than 1. So so make the beta 3b as beta I don't know 5b. Okay, so let's just make it really big. Okay, apologies for that. I think I should have been careful when I saw that. So this should not go to 0.75. That's not a good thing. So make it beta 5b so that your calculations are a bit more decent. Yeah, that's better.
5B or 2B, sir?
I'm sorry?
5B or 2B?
5b. Let me put that out here in the chat box. Just hold on 1 minute. Beta 5 comma b. Okay. Apologies for that.
Thank you.
Okay, so in the interest of time, let me just see the responses. There are about 13 responses. Yeah, 0.68. Somebody, I think 0.68. Some people are getting. So maybe let me just work this out and see how it goes. So did you get b equals 5 by 4? Is that okay?
Yes, sir.
Right. Okay. So b is 5 by 4, and then your posterior is going to be proportional to the prior. Prior is what? P power 4 times 1 minus p power 1 by 4, right? This is your prior, which is beta 5b times likelihood. Likelihood is what? 6 of them had benefit out of 10, right? So p power 6, 1 minus p power 4. Okay. So you get p power 10, 1 minus p power 4.25, maybe this one. Okay. So p hat Bayesian in this case with one very biased thing is going to be 11 by 11 plus 4.25. Is that okay? Did people get something like this?
Yes, sir. It's fine.
No, sir, it will be 5.25, no?
Yeah, you're right, absolutely. Yeah, so 16. I was about to make that change. 16.2. Is that okay?
Yes, sir. It's approx 0.67.
Okay, 0.67. There you go. So this is what you get because of the biasing that we did. So if you don't bias, you want to go to p hat mm or ml, what will you get? You'll get 0.6. Right? So you can see there's like a slight difference because of the bias that we did. Okay. So I hope this part is clear to you. So the last few questions are a bit more representative of the kind of questions you'll get in the exams. But the first survey part, I hope, was also interesting to you and getting to understand how these things work out when you actually do survey, collect information, and see how quite a few interesting results we saw. How non-representative samples can lead to very misleading results, even if you use the statistics. Even if you don't make any mistakes in the statistical method, just because the data does not fit the model you're using, you can get very misleading results, and one needs to be very careful about all this. Okay. All right. So I'm going to stop today. If there's any questions or comments, maybe I will just ask if somebody has anything.
Thank you very much. It was a very nice session.
Okay. Thank you. Thank you. Thank you, and good night, and all the very best for your exams. Do very well. I think most of you, if you prepare well, make sure you see all the problems, then you should do well. Okay.
Yeah, may I ask you one question, sir?
Yes, sure, please.
The difficulty level of the statistics is, I think, highest up to this foundational level. I think so, for me, at least.
Okay.
Whether the other question papers in the future examinations will be of this difficulty level or more than this, double of this or like that, so that we can plan. We are professional people. We are not able to plan whether we should continue totally or not.
Okay, so Stats 2 is generally considered the most difficult course. Most people find it the most difficult. So, but just going based on the statistics of pass percentage, let's say, right? Stats 2 is
not only through foundation, sir, up to the BSc.
Yeah, up to even including diploma. Diploma courses have very high pass percentage. That's the information I can give you based on statistics.
Yeah, because planning part is required for professionally. We have to spare time. If you don't spare time, then it is not possible.
Yeah, you have to spend time. That much I'll tell you, guaranteed. Even at the diploma level, you have to spend time, because many of them will involve a lot of hands-on work, a lot more hands-on than what you've done in the
Other papers are not more difficult than this statistic.
Yeah, I don't think they're difficult.
Okay.
But time will be needed. You will have to spend time.
Okay, no problem. Time, we will spare time.
Okay. Okay.
Thank you. So nice of you.
Thank you. Bye-bye. Okay. All right. Thanks. Bye.
Right, sir.
Good night.
Okay. Good night, everyone.